So good morning, and this week's videos we are looking at the last few pages in the Halogenoalkanes notes. So the work for this week will be to complete these notes and the questions at the end of the pack for uploading by Friday, please. So we're just going to take you through the substitution reactions, including the Sn1 and the Sn2 mechanisms, looking at core practical 4, which is looking at the rate of hydrolysis, and we're also going to be looking at the elimination reactions, and that will complete this pack. So in today's video we're just going to start looking at substitution reactions, looking specifically at Sn1 and Sn2. Now we've covered these already before in the optical isomerism pack, so you might want to just have a quick read over that before we start. Okay, so we're on page 10 of your notes, and we're looking at the substitution reactions of the halogenoalkanes. Most of the reactions we're going to be coming across in this pack are these substitution reactions. So we need to just define what is meant by a substitution reaction and what is meant by a nucleophile. So a substitution reaction, it does exactly what you think it is. It's a reaction where an atom, or more usually a group of atoms, is replaced by another atom or group of atoms. So for example, we can replace a Cl with an OH. That would be a substitution reaction. Cl group coming off and the OH group going on. A nucleophile is very simple. It is a species with a lone pair of electrons. That's the basic definition of a nucleophile. It has to have an available lone pair of electrons. So I'll put available in there. In other words, I can use them for something, so they're available. So examples of this would be the hydroxide ion, it would be ammonia, it would be water, it would be the cyanide ion. So all of these have lone pairs of electrons on them which are available for us to use, and that makes them a nucleophile. So the first reaction we're going to be looking at is the reaction of the halogenoalkanes with dilute aqueous alkali. So that's sodium hydroxide, potassium hydroxide, and a chloroalkane. So it has to be dilute and it has to be aqueous. Okay, that's very important because there's going to be a different reaction if that is not aqueous. So what we're going to do is dissolve our halogenoalkane in ethanol. Then that may sound a bit weird when we're doing the reaction in water, but ethanol is what we call a co-solvent. Okay, because the halogenoalkane, we looked at this in one of the first videos, they don't dissolve in water. So if I have an aqueous reagent and an organic reagent, those two aren't going to mix, and we've got a bit of a problem. So we add some ethanol. Ethanol is a good co-solvent because it has both polar and non-polar characteristics. So it's polar enough that it will take water into solution by doing hydrogen bonding, but it will also be able to dissolve in the halogenoalkane. So both of those will be able to dissolve, and they'll be able to mix together. So quite often in these reactions you will see ethanol there as I said, as the co-solvent. Okay, so we're going to have just a look at this reaction. So we're going to use chloromethane CH3Cl, and I add my sodium hydroxide, and I'm going to make sodium chloride NaCl, and I'm going to replace the Cl with the OH group. So if I show the ionic equation for this, leaving out the spectator ions but drawing in all the bonds, I just get the basic reaction of making my alcohol, and I've got my Cl negative ion that's come loose. So I've substituted my Cl with an OH, and because of the lone pair on the OH, that's what's doing the attacking. This is an example of a nucleophilic substitution mechanism. Okay, So we have this mechanism, and one of the first steps we're going to have to do, or at least at one point, we're going to have to break this bond here, this carbon-chlorine bond. So there's really two things we need to consider. We need to consider the polarity of this bond, because this is going to be delta negative and this is going to be delta positive, and this is what's going to be attracting that lone pair. So we need to consider the polarity of this bond, but also we need to look at the strength of this bond, how easy or hard it's going to be to break it. Okay, so if we look at the bond dissociation enthalpies, we can see that as you go down the group, it becomes easier to break the carbon halogen bond. The reason for this is just down to the size of the atom. So fluorine is quite a small atom, it can get quite close. We've got a short bond here. Remember, short bonds are very hard to break. By the time we get down to iodine, it's quite a weak bond because the iodine is a large atom. So considering this on its own, we would expect the substitution reactions to happen more readily or more quickly as we go down the group. So as you progress down the group, the reactions would happen more readily. They'd happen faster. And they happen more readily because the bond is weaker. So as we go down the group, the halogen gets larger, therefore the bond length gets longer, therefore the bond becomes weaker and less energy required to break it. We're going to look at the Sn1 mechanism, and this works with tertiary halogenoalkanes and has one molecule, we say one species, involved in the slow step of the mechanism. Overall, it is a two-step mechanism, so there are two reactions really going on. So we're going to start with 2-chloro-2-methyl-propane, which is a tertiary halogenoalkane. So I have my 3 CH3 groups around the carbon. This is a polar bond, so this is delta negative, this is delta positive. Okay, now we talked about this a little bit in the isomerism pack, so do go and look at that if you're still not sure about it. But these big groups here, these methyl groups, are quite bulky. So this poor little OH group can't attack that delta positive carbon. It can't get at it because it's being blocked by these big chunky groups getting in the way. So what it has to wait for, and that's why this is such a slow step, is it waits for this bond here to break. Now very few of the molecules will have enough energy to do that. It's a very high activation energy, this step. So, but this bond can break. It's long enough that it can break. So I'm going to get a CH3 groups around here. And my Cl negative has come loose. And that's step 1. So I'm just going to call that step 1. This is why we say it's a two-step reaction. Step 2, we're going to start here with the carbocation. So I'm going to start with my carbocation. This is a tertiary carbocation. Makes it very, very stable. It's called the inductive effect. So I've got 3 methyl groups all weakly donating with 3 alkyl groups all weakly donating, slightly reducing that positive charge on that carbon. I have my OH, my nucleophile with its lone pair, which I'm going to bring in, and I'm going to put in there. Okay, so this step is very fast. So we have a slow step here, because very few particles have an energy capable of doing this. But then this step, because you're attracting a positive and a negative, is very, very fast. And you get your product. You also get, remember, CH3, CH3, and a CH3 there. So you've got your your CH3 groups bonded onto that central carbon. And that's your tertiary alcohol. You've still got some of your chloride ions, they haven't disappeared, they're still there. So you get sodium chloride or potassium chloride or whatever you used there with your OH negative. So the stability of the intermediate carbocation, well, it's a tertiary, so it's very stable, or it's more stable than the others because it has 3 alkyl groups, or weakly electron donating. So each of them can kind of lend this carbon in the middle a little bit of their own electrons, and that's going to make it nice, and or it's going to make it more stable than the secondary or the primary. It's still not as stable as the whole molecule, but it's very stable compared to the other carbocations. Okay, so now we're going to look at the Sn2 mechanism, which is for primary halogenoalkanes. So we're going to start with some chloroethane, and again we're going to react it with aqueous sodium hydroxide. So we're going to start with the chloroethane. It's primary, so it only has 1 R group, this methyl group here. Still got my delta negative and my delta positive, but this time the carbon I'm trying to attack is only, if you like, being protected by these tiny little hydrogens. So much more of this carbon is exposed to the attack, so I can attack it directly. I don't have to wait for this chloro group to come off. Also, if I tried to do this via an Sn1 mechanism, I would have to form a primary carbocation here, and that primary carbocation would be very, very unstable. Very difficult to form. It's got a very high activation energy, so it's more energetically favourable for it to go via this Sn2 mechanism. So I've got my OH negative with my lone pair on it, and 2 things happen simultaneously. The lone pair attacks that carbon, so that's attacking into that delta positive area there, and that pushes the electrons in the bond onto that chlorine delta negative. So we get this funny little looking thing which we put inside a box. So we've got the carbon that's being attacked, and I'm just going to put the other groups sort of above and below it, sort of keeping them out the way almost. Then we've got our 2 dotted lines. This is showing this bond is coming in as this bond is going out. So we have the OH group coming in as the chloro group is going out. Now somewhere inside there is a negative charge because it's being transferred from the hydroxide, the OH group here, over to the chlorine, but I don't know quite where it is at this point, so I'm just going to put it on the outside of the box because I know it's in there somewhere. I'm just not quite sure at this stage where it actually belongs, so we're just going to sort of put it on the outside. Couple of things to point out with this mechanism which are very common errors. Common error number 1 is not to have this at the right bond angle. You have to have this OH group coming in the opposite side to the chloro group. So that bond angle here between these 2 groups must be, or between these 2 bonds I should say, must be 180. Okay, so you've got to have a 180 bond angle between the incoming and the outgoing group. So it should be 180 between those 2. The other is the orientation of this OH group. Watch, you've drawn it round the right way. So it is the oxygen which is bonding to the carbon, not the hydrogen. A number of times I've seen that written round the wrong way. And then our overall product, well, our OH group has now joined on, so we have our ethanol as our organic product, and our chloro group has now come loose and now has that negative charge. So basically we're charge balancing it all the way through, and that would now be sodium chloride if I started with sodium hydroxide, or so on. Okay, so this is just one step. This isn't counted as an intermediate, this is a transition state. So it's just one fast step. Okay, this is a unitary response, just 2 things reacting together, and it forms a one fast step. So there is no slow and fast steps in this because it's all one step. Okay, so that just looks at the beginnings of the reactions of the halogenoalkanes, concentrating on the Sn1 and Sn2 mechanisms. In the next video, we're going to be looking at the hydrolysis reactions and what determines their speed, the rate of their reaction. And we're also going to go on and look at the other substitution reactions using nucleophiles. But until then, take care, stay safe, bye-bye.